Here we're going to start off by looking at patterns of flight paths for projectiles and then go on to look at how we can represent those using free body diagrams and parallelogram of forces diagrams. So a flight path of a projectile is either described as parabolic or non-parabolic. So once it's released, the projectile follows a flight path determined by the forces acting on it. And we said before that this might look something like this, or like this, or it may well, the flight path, the trajectory, look like this. If a projectile is unaffected by air resistance, it follows the shape of a parabola, which is a uniform curve symmetrical about its highest point. And both of these examples are examples of parabolic flight paths. Whereas if a projectile is highly affected by air resistance, it's going to follow a non-parabolic flight path, a non-uniform, non-symmetrical curve, such as this one. So a shotput is a really fine example of a projectile which is unaffected by air resistance, or air resistance is very, very small. Weight is really dominant on a shotput because it's obviously a heavy object, and therefore it's going to give us a parabolic flight path. So with a shotput, we're going to have a flight path that looks something like this, and I would label it symmetrical because obviously it is hard to draw a perfectly symmetrical shape like that. So I would point on the fact that we've got the highest point here, and then we've got what we call a uniform curve. Okay, the curve looks the same at this side as the highest point as this side. I've drawn a positive release height because obviously it's a shot put, but in terms of the curve, it's uniform, it's symmetrical. With our badminton shuttle, we get the opposite of that effectively. So our flight path with a badminton shuttle looks more like this. It goes up into the air, but then there will be a point where it will drop. It's asymmetrical. So again, on this one, we've got our highest point. And we've got a non-uniform curve, which means that from the highest point, we've not got the same happening on this side as we did with our parabolic flight path. So a parabolic flight path, one that looks like this, or like this, or like this, they're all symmetrical, and I would make sure I labelled them as symmetrical because I'm not sure that really looks symmetrical, is when weight is the dominant force acting on the projectile and air resistance is having very little effect. And a shot put is a perfect example of that because it's got a very large weight, but it's travelling slowly with a low velocity. It's got smooth surface characteristics, and it's got a small frontal cross-sectional area, and therefore air resistance is low. Whereas with a shuttlecock, a badminton shuttle, it has a very low weight, but it travels at high velocity through the air, and it's got uneven surface, rough surface characteristics, which makes air resistance very high. When air resistance is the dominant force, then we get this non-parabolic flight path. And so we can draw that, we can use a drawing, a free body diagram, just like we've done before in year 1 when we looked at drawing forces on a body. We can draw the force arrows on a projectile to represent which forces are acting, and you will already know that. The size of the forces that are acting on the projectile, which direction those forces are acting, and where they're acting from. And again, most of those things you will already know. This is going to be revision. The reason for doing it for a projectile is because it allows us to calculate the net force acting on the body and therefore the resulting projectile motion. We know already they're called free body diagrams, these diagrams that show forces. weight is not going to change, and that's really important to remember. The shot put and the badminton shuttle, the weight doesn't change once they're thrown into the air. Weight's going to remain constant, but air resistance would change. Can you think why air resistance would change? Thinking about factors affecting air resistance. So obviously, we know that as a badminton shuttle is hit, it is at its highest velocity as it leaves that badminton racket, and from there on in, it is decelerating, and therefore its air resistance gets smaller and smaller as it travels through the air. Similarly, with a shot put, it's at its highest velocity as it leaves the hand of the athlete. From there on in, the velocity is getting smaller and smaller, and therefore air resistance becomes smaller and smaller. So with these free body diagrams, they show the force acting on a projectile. They're drawn usually for the start, the middle and end of a flight. We're always going to remember to keep the weight arrow the same length because weight doesn't change, and we're going to draw weight acting from the centre of mass acting downwards. You know that already. We're going to draw the air resistance arrow in the opposite direction to motion. Remember, and you know that already, acting from the centre of mass. But we need to think about whether we're going to decide whether air resistance is the larger force acting on the projectile, or whether weight is the largest force. So we're going to start with one with a shot put. We're going to draw the start, the middle and the end of the flight. We're going to draw the forces acting on that projectile to represent which forces are acting, the size of the forces and the direction. Weight isn't going to change. So let's have a think about it before we draw it. We know that at the start of the flight, velocity is at its highest, so air resistance is going to be at its largest at the start, and then mid-flight and to the end it's going to become smaller and smaller. But if we think about a shot, it's heavy, isn't it? It's in comparison to the force of air resistance acting on it, weight is going to be a dominant force, and it's going to be that throughout. So my weight arrow is going to be quite big at the start of the flight, and it's not going to change throughout. And that is going to cause this what causes this parabolic flight path. So I'm going to draw the flight path first, because I know that a shot put has a large weight and a small air resistance. So I've already decided it's going to be a parabolic flight path. Okay, so I'm drawing my parabolic flight path. And then I'm going to draw my shot put on towards the start, the middle, and towards the end of its flight. First force that I'm going to draw on this shot put is going to be weight. That's the easiest one, I think. And I've already decided that weight is a big force acting on this shot put, and then it is not going to change throughout the flight because the shot put isn't getting heavier, nor is it getting lighter. Then I'm going to draw on my air resistance. Now, this is a bit more complicated than air resistance that we drew in the past, because we've now got the direction of motion of this projectile is changing. So at this point here, the direction of motion of the shot is like this, whereas when it's up here, this is the direction of motion, and when it's down here, this is the direction of motion. So I need to then draw my air resistance arrows in the opposite direction. Now, my first air resistance arrow is going to be the biggest one, but it needs to be smaller than weight, because weight is the bigger force acting on a shot put. So I'm drawing air resistance in this direction, shorter than weight, but it's going to be bigger than the next two. So by the time we've got to this point in the flight, air resistance has grown smaller due to velocity growing smaller, and by the end, air resistance arrow is going to be very small because the velocity is very small. Okay, so that gives me my parabolic flight path, and we're going to look at how we actually decide that next. Shuttlecock this time. So at the start, the velocity is at its highest. We know that again. So air resistance is going to be at its biggest at the start. Velocity declines, so air resistance falls. And by the end of the flight, by the end of it, air resistance, like the shuttle has almost stopped in the air, so air resistance becomes very small, and we end up actually towards the end of the flight with weight becoming the most dominant force, and that's the thing that causes the shuttle to drop to the floor in the end. So let's have a go at drawing that one this time. I'm going to draw my non-parabolic flight path in first. So we're going to come up and then we're going to drop effectively to the floor. This time we've got a shuttle, so we've got the head of the shuttle and its feathers, and then the middle of the flight path we've got again the head of the shuttle and its feathers, and then towards the end we've got the head of the shuttle and its feathers here. Okay, so again I'm going to draw weight on first just because that doesn't change, but this time my weight arrow is going to be much smaller than it was when I drew weight from the Shotput and weight. So I'm trying to make sure they remain in the same size, and I'm just going to change that. Oh no, I'm just going to, I wanted to change that weight arrow because I don't like where it's acting from, because on a shuttle the centre of mass is inside the head of the shuttle, not the feathers. Okay, so now I'm going to draw my air resistance arrows and my direction of motion. So I've got direction of motion, still the direction of motion, maybe slightly flattened out, and now by this point, direction of motion. So at the start, air resistance is big because the velocity is high, and air resistance is bigger than weight. By the middle, air resistance has shortened, but it's still bigger than weight. It's still not being dragged to the ground. Whereas by the end of the flight path, air resistance is now smaller than weight, and it's causing the shuttle to drop to the ground at that point. And this is what's making this a non-parabolic flight path in the end. Okay, so we've got large velocity at the start, which equals a large air resistance. Weight is constant. Obviously, weight doesn't change. Air resistance falls because velocity falls. Weight becomes bigger than air resistance at the end, which causes the shuttle to drop. And that's the result is that non-parabolic flight path. So really, with the object that you're given, it might be a shuttle, it might be a Shotput, it might be something else. You need to think and decide whether weight is going to be the dominant force. Is this a reasonably heavy object with a small frontal cross-sectional area with a smooth surface that's travelling quite slowly? Or is it quite a light object that's travelling quickly through the air? Deciding whether we're going to be getting weight as the dominant force or air resistance as the dominant force, and therefore whether we get a parabolic or a non-parabolic flight path. Now we can use the next bit to help us to decide that, and that is where we're going to look at this resolution of forces acting on a projectile in flight using a parallelogram of forces diagram. Now honestly, that sounds more difficult than it is. So we use this parallelogram of forces diagram to decide whether what the resultant force is that's acting on the body. What are the sum of all the forces acting on the body, and what is the result in terms of the flight path? So the resultant force shows the acceleration of the projectile and the direction of that acceleration, and the flight path, whether it's parabolic or non-parabolic. And we're going to use those same examples of a shuttle and a shot to help us work through that. So if you compare free body diagrams to a parallelogram of forces diagram, remember on a free body diagram, it shows all the forces acting on the projectile. It's drawn for the flight of the projectile at the start, the middle and the end. We keep the weight arrow the same all the way through. It acts from the centre of mass directly down. We always draw the air resistance arrow in the opposite direction to motion, acting from the centre of mass. And we need to decide whether air resistance is larger than weight or whether weight is larger than air resistance effectively. With a parallelogram of forces diagram, we're showing the resultant force. And it starts in exactly the same way. It starts with a free body diagram, but then we're going to add broken lines to create a parallelogram from the force arrows, and then a diagonal line which shows us the direction and the size of the resultant force. And we need to remember these two rules. If the resultant force is closer to weight, weight's the dominant force. If the resultant force is close to air resistance is the dominant force. When compared to the direction of motion, which direction the result, we will answer that question as we go on. Okay, so let's think about parallelogram of forces diagram for a shot put. First of all, so we're just going to take one time we can talk about the mid-flight of the shot put, okay? And when we drew that shot put, we had weight as a really large force acting downwards, and then we had air resistance acting in this direction, in the opposite direction to motion, okay? So our parallelogram of forces diagram starts exactly like a free body diagram. We're going to draw on the two forces acting, weight and air resistance. Then we need to add a broken line to make this into a parallelogram. So, and it needs to be a broken line because it's not a force line. So we're going to draw one line that is parallel to the weight arrow line, and then another line which is parallel to the air resistance line, and that has now made a parallelogram. Okay, and this is as easy as that, the parallelogram of forces diagram. But we then need to add the diagonal line, which is the resultant force. So now this is not a broken line anymore, and we draw it from where air resistance and weight are acting, so from the centre of mass out to this opposite corner. Okay, so we're going to draw a straight line out here, and this is the resultant force. Okay, now then, if we go back to that rule, if the resultant force is closer to weight, weight is the dominant force. If the resultant force is closer to air resistance is the dominant force. Well, here we can clearly see that air resistance is closer to weight. The resultant force is closer to weight than it is to air resistance, okay? And this means it's going to give us a parabolic flight path. It also shows us that the direction of motion is this way, but actually the resultant forces are dragging this shot put backwards and downwards, and that shows that the shot put is decelerating. Because the resultant force acting on this shot put is this way, and the direction of motion is that way. So it must be that the resultant force is pulling it backwards, and therefore that shot put is decelerating. And we know that's true because once that shot put is released from the hand of the thrower, all the time we know that that shot put is decelerating. Let's think about parallelogram of forces diagram for a shuttle then. And by the way, we don't have to draw actually the shuttle in. So your parallelogram of forces diagram would just really look like this: air resistance, weight, a broken line, and your resultant force. Okay, and that really is your parallelogram of forces diagram. So if we do the same for a shuttle, so again we've got that shuttle mid-flight. Okay, we're going to draw on our weight arrow first. This time weight is small. We're going to draw on a really big air resistance arrow, so we're thinking about a shuttle at the start of its flight. So air resistance is large. And now I'm going to draw on that parallelogram with a broken line, and then that resultant force arrow. Okay, if I were in the exam, I may well have just drawn air resistance, weight, a broken line, and the resultant force. Okay, so this is fine. We don't need to draw really the shuttle in. It's just for demonstration purposes. So again, if the resultant force is close to air resistance is the dominant force. And with air resistance here, clearly the resultant force is nearer to air resistance than it is to weight, and that gives us a non-parabolic flight path. Now, we've still got the direction of motion this way and the resultant force this way. So again, it's showing that this projectile is decelerating. And again, we know that to be true because the highest velocity for the shuttle is as it leaves the racket. From there on in, that shuttle is decelerating. So we're going to have a look at a few exam questions on this now. So identify two factors that affect horizontal distance travelled by a projectile. Pause the video and write down two possible answers to that question. 2 marks. So hopefully you would have got one of the top 3 here: height of release, speed of release, and angle of release. We're going to look later at how aerodynamics, so the air resistance acting on it, the shape, the spin, how that can also affect the horizontal distance travelled by a projectile, but you'd have picked up 2 marks on this by just knowing height of release, speed of release, and angle of release. Okay, question number 2. In the Shotput event, the shot becomes a projectile when it's thrown into the air. Explain 3 factors that affect the horizontal distance travelled by a shotput in flight. 3 marks. The difference with this question is the explain, okay? So in the first question, we only had to identify just a list. There's something different about this question. It's requiring you to explain. So simply saying height of release, speed of release, and angle of release isn't going to be enough in this explain question. You need to say how those factors are going to affect the shot put specifically. So pause the video, 3 marks. So yes, you would have started off by saying speed of release, but then you had to explain that. So the higher the shot put, the higher the speed or the velocity of release of the shot put, the further the horizontal distance. So that is to explain rather than to just list or to state. Again, angle of release. Well, when we talk about a shot put, just less than 45 degrees is the optimum angle because we've got that positive release height. So just to say angle of release wasn't good enough here because we're explaining about a shot put. So we had to be specific about the shot put in our answer. 3rd mark, height of release. The greater the height of release, the greater the distance travel, okay? You might have then referred to the fact that in shot put we have a high height of release because the height of release is greater than the landing height. You might have gone into that detail. You didn't necessarily need to get those 3 marks. Okay, explain the shape of the flight path of the shot put. Again, we've got this word explain. So to simply state here that the shot put is going to travel, is going to follow a parabolic flight path isn't going to be enough to get the marks for this explain question, which is 3. it might allow you to pick up 1 but not 3. So explain that parabolic shape. What causes the parabolic shape of the flight path for a shot put? Okay, so for a shot put, it's parabolic or nearly parabolic, symmetrical flight path. The reason why it's saying nearly there is because obviously air resistance does act on a shot put. It's just very low because it's travelling slowly, it's very smooth, and it's got a small frontal cross-sectional area. The reason that we get a parabolic flight path is because weight is the dominant force. Weight is greater than air resistance. Air resistance is very low or it's negligible because of the low speed or the smooth surface or whatever, okay? You might have drawn a parallelogram of forces here that show that weight is the dominant force over air resistance, okay? And you might have shown then that the resultant force is closer to weight, which gives us that non-parabolic, which gives us the parabolic flight path. But what you're essentially showing there is that weight is the dominant force over air resistance. Because weight is bigger, it makes the resultant force closer to it, giving us that parabolic flight path. Sketch a free body diagram in the box below showing the horizontal and vertical forces acting on a football in flight. Now, it's not asking you to talk about the start of the flight, the middle of the flight, the end of the flight. So one sort of drawing here was good enough. So think about a football, think about weight, think about air resistance. I think this was worth 2 marks, I believe. Okay, so you could have drawn, your drawing might have looked like this, it might have looked like this. It didn't matter as long as you drew on the direction of motion and then air resistance was in the opposite direction. If you haven't drawn direction of motion, your air resistance arrow doesn't make any sense. So air resistance from the centre of the ball acting in the opposite direction of motion, and that was really important. So if you drew this ball going that way, then your air resistance this way. Obviously in this example, the person's drawn the direction of motion this way as if it's been just sort of kicked off the ground, and therefore air resistance acting in the opposite direction. And then the second mark for weight acting vertically downwards. There were no marks here about the size of the weight or the air resistance arrows, and it's quite difficult actually for a football as to whether air resistance is the bigger factor or weight. But I would say air resistance is bigger on a football because a football is travelling so quickly at such high velocities. A football isn't very heavy, so its weight, the effective weight is quite small, but it can be travelling at very high velocities, and therefore air resistance is going to be quite large. Which brings us to the next question. Sketch a diagram in the box below to show how you would represent the resultant force acting on a football in flight. So now to show the resultant force, we need a parallelogram of forces diagram. Okay, so pause the video, have a go at that one. So this time it's 3 mark questions, sorry, I forgot to say that in the introduction. So we've got, again, air resistance and weight are from the same point. There's no football on this one. We've just got air resistance and weight. That can be, that doesn't have to be a dashed line. We then have dashed lines to create the parallelogram. Gave you another mark. If you didn't use dashed lines to create a parallelogram, you didn't get the mark. Also, note that if you just drew the resultant force, you don't get that 3rd mark. Okay, so we need the dashed lines for the parallelogram of forces, and we need the resultant force arrow, again originating from the same point as weight and air resistance into the opposite corner. And for this one, it's not asking actually, but if it did, we could say that the resultant force is closer to air resistance than it is weight, and so this football would be having a non-parabolic flight path. Okay, last question. Oh no, that's for later. So that's it for this video. That means that we have now covered all of this projectile motion content. So from today's lesson, factors affecting the horizontal distance travelled by a projectile, free body diagrams, resultant resolution of forces coming from parallelogram of forces diagrams, and then these parabolic and non-parabolic flight paths that we see in shot puts and in badminton shuttles.